Band subset selection and non-negative matrix factorization method for hyperspectral unmixing. In this project, a fast independence components analysis method is used for selecting the most independent bands from the image hypercube in Python. The non-negative matrix factorization method is used for unmixing, which is also implemented in Python. An RGB image is visible to the human eye because the wavelengths of the reflected light are within the visible range 400 to 700 nanometers. A hyperspectral image is recorded by sensors that can capture reflected light from wavelengths beyond the visible spectrum, called the infrared, shortwave, and longwave infrared regions ranging from 700 nanometers to 12 micrometers. Hyperspectral image bands beyond the infrared cannot be seen by the human eye, but three bands can be selected and displayed as an RGB image. Hyperspectral images acquired by satellites that orbit the Earth have poor spatial resolution. That is, each pixel covers a square area of about 30 meters on ground. Hence, each pixel will have recorded light reflected from different materials on ground, such as water, dirt, asphalt, and such or vegetation. Hence, these pixels are called mixed pixels. The fraction of the amount of material imaged in each pixel is called spectral unmixing. Each material, such as water or green vegetation, have their own spectral signature. There's a spectral library of pure materials, and these pure material spectra are called N-members. Equation 1, the linear mixing model, postulates the mixing of spectra imaged by the sensor as a linear model, where Y is the resulting pixel, Sk is the kth N-member out of a total of R, Ak is the abundance of the kth N-member, and W is additive noise. Additional constraints for this model include that A is also non-negative, and the sum of rows is less than or equal to 1. The hypothesis underlying non-negative matrix factorization is that latent features of the original non-negative dataset can be extracted in an additive model where components are also non-negative, preferably sparse and unique. The NMF for non-negative matrix Y is modeled as Y equals A times B transpose plus E, where A is the basis matrix and B is the encoding matrix. It is clear that A, B transpose, and E in equation 2 are analogous to S, A, and W respectively in equation 1. Under the assumption that the non-negative y is the sum of linear combinations of non-negative parts, one can hypothesize that a factorization exists where we can recover the parts or the bases and how to combine them in an encoding matrix in order to approximate y. The manner in which this algorithm is run is that first you consider Y a data cloud consisting of n data points in an m-dimensional space. The dataset can be enclosed in a cone A outlined by R edges, and this cone is shrunk so the edges just touch one or more points. The smallest cone that still encloses the data is likely to be unique. The edges of the cone, called extreme rays, are the basis vectors in the columns of A. For pre-processing, band subset selection was conducted using independent components analysis, or ICA. This method evaluates the weight matrix to observe how each band contributes to the ICA unmixing procedure. First, it compares the average absolute weight coefficients of individual spectral bands and selects bands that have more information. Then, it retains most physical features of the spectral profile, given only the observations of the hyperspectral images. The ICA unmixing model is given by S m by p equals W m by n times S n by p, where m is the number of source signals, n is the number of observed signals, S is the observed signal, S is the source signal, and W is the matrix. The objective function is given by JFX. The weight vector is decorrelated from p weight vectors using the following pair of equations, W plus sub p plus 1 and WP plus 1. So this is the implementation of ICA in Python using the sklearn toolbots. First, the signals are reconstructed, and then you get an estimated mixing matrix, and you compute the rank of the matrix, and you get the pseudo-inverse. And then the transpose of S is used to compute a weight per band, and the indices are extracted, and the selected bands are outputted by the function. Hypercube decomposition is conducted by taking an image cube Y with the band selected by ICA and breaking it down into a product between the abundance cube A and the spectral matrix S. First, the error y minus a squared is minimized and a multiplicative update is conducted to solve the NMF problem. A is continually updated while keeping S fixed, and then S is continually updated while keeping A fixed. These updates are applied until convergence is achieved. Okay, so this algorithm is supervised and the number of n members are fixed. First, the A and S variables are initialized, and then the convergence tolerance is defined. The maximum iterations is defined in a variable, a counter is set up, and a while loop is used to run the algorithm until convergence is achieved. The convergence is continually checked, and the algorithm is run until we reach the desired result. Okay, so here you have the code for loading the data and entering the number of bands. The data set that was used is of the Jasper Ridge, so you have multiple elements here that are shown in the original image, which is 100 by 100 pixels and contains 198 bands. You have water, you have road, you have vegetation, you have dirt, and in the bottom left, you can also see the spectral decomposition of the n members in the ground truth. Um, so the data set is loaded. You load the ground truth n members, and you reshape the data into a two-dimensional matrix, and you define um the n member classes, which in this case are tree, water, dirt, and road. You get the length of the n members and the number of n members or components in the image. These signals are then reconstructed, and you get the estimated mixing matrix. Here you also have the code for computing the ICA. And um, the output displays the selected bands. Okay, so here you have the function for computing the NMF. First, you solve the linear unmixing problem and you compute the abundance matrix, and you continually update them and you update the n members as well. You initialize the linear relationships as well as the abundance matrices and the n member matrices, and you normalize the arrays for the n members and the spectra, and you compute the error, and it returns the arrays WH and the error. The error is initialized in the code for calling NMF, and the maximum number of iterations is 200. And then you compute the error for each iteration and the W value and H value as well, and you print it. And then after that, the results are plotted, and that is shown to the right. So there are about 59 iterations, and the minimum error is 8.57. Okay, so here you have the plot of images and abundance matrices. Here we define the function for displaying the hyperspectral image as an RGB image. You extract the number of rows, columns, and bands from the original image, and then you assign the number of bands to use for averaging to display the processed image. And you assign the average of each of 30 bands to the blue, green, and red colors, and you stack them, and then you normalize all of the values. The abundance matrices are then plotted. So first you get the size of the A1 matrix, and then you extract both abundance matrices, you define the n member classes, and you plot the ground truth abundance images along with the estimated abundance images, and that is shown to the right. Okay, so summary and conclusions. The first one is that by unmixing, you can extract two types of information that are obtained from the hyperspectral image. The first is the composition and spectral bands for each pure pixel or n member, and the second is the abundances of the pure pixel for each hyperpixel. The unmixing results have been improved by implementing a pre-processing step for band subset selection using independent components analysis, which is translated into code. And this implementation uses a supervised multiplicative update method for non-negative matrix factorization, where the number of n members is pre-specified. Thank you so much for listening, and here are my references.